A chemical reaction is like a recipe in the real world. And as an example of this, let's say that you wanted to bake a cake or something like that. Well, you'd have to know how much flour to add, and if you needed an egg, or if you needed milk or soy milk, whatever you happen to put in. Honestly, I have no idea what's in a cake, I'll be honest. But anyway, that's the right idea. And at the end of that, if you followed the directions, you would end up with a cake. I like cake. Anyway, a chemical reaction is somewhat similar. Of course, you're not making cakes, which is no fun. However, that black reaction right there, what it is it's like a reaction, a recipe for a chemist. And it says that you need 4 parts aluminum and 3 parts oxygen to make 2 parts aluminum oxide. Now, if this was a recipe in America, it might be cups or something like that. In the chemical world, this is moles. So you would need 4 moles of aluminum to react with 3 moles of oxygen, and that will end up making 2 moles of aluminum oxide. This is a balanced chemical equation, or a balanced chemical reaction, same thing. And there's a lot of cool symbolism that comes around from this. Now, first of all, in a recipe, you would put the flour and the eggs and the milk or whatever together, and that would make the cake. So in that case, the flour, eggs, and the milk would be the reactants, the part you put in, and in that case the cake would be your product, like what you get out. Well, in my chemistry world, notice there's an arrow there, and things to the left of the arrow are the reactants, the part you put in. So we'll put in aluminum and oxygen in this case, and then to the right of the arrow, that's what we call the products, and those are the parts you're going to get out. So you're going to get out aluminum oxide. And you can probably see there's lots of cool information in there. First of all, those big numbers in front aren't really parts, they're moles. Like I said, they're called stoichiometric coefficients, and you don't have to ever spell that or anything, but stoichiometry is the measure of quantity, like how much goes in, stuff like that. And for chemists, that's always going to be moles. The other part, though, you might have picked up on there is that there's S's and G's, and S stands for solid, so that would be aluminum solid. It wouldn't be aluminum as a gas or a liquid or something like that. That being said, the O2 there is a gas. You wouldn't put in liquid oxygen or something like that. You would put in gaseous oxygen. And on the other side, the product, the aluminum oxide, you're going to get a solid out. So in chemistry, you'll definitely see S for solid, G for gases. You'll also see once in a while L for liquids, specifically water is very common. And AQ stands for something that's dissolved in water. So a solution, like we talked about in the last chapter. So for example, you could have a sugar solution, sugar in water. We would write that in chemistry as sugar AQ. All right. So anyway, a lot of power comes from this, and we'll talk about what chemists can do. You have to have a balanced reaction. I'll tell you some techniques how to make sure that your reaction is balanced. It's pretty cool. This is another example of a balanced chemical reaction. It's phosphorus plus chlorine making phosphorus trichloride. The reactants are on the left. Phosphorus, which is actually P4 in the real world, is a solid. You're going to add that to chlorine gas. You can see there's a G right there. And that's going to make phosphorus trichloride, which is a liquid. And sometimes you see that fancy cursive L right there for liquid. Sometimes you see just a regular lowercase l, but they're all the same. And again, you can see how there's 1 P4. There's no 1 there, but that's implied. You'll need 6 Cl2s and 4 to make 4 PCl3s. So the invisible 1 by P4, as well as 6 and 4, those are the stoichiometric coefficients, and they tell you the relative amounts of moles that you need. I also think it's relevant at this time to remind you about the 7 diatomics, which we mentioned in an earlier lecture. The 7 diatomics are have no fear of ice clear brew, hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And those always exist in pairs. So in the last slide, there was O2. In this slide, there's Cl2. If you see one of those, it's going to be really important in this chapter that you write it as a diatomic. Don't write just Cl. Most of the elements, honestly, you can write as them. Phosphorus is an example of what's called a tetramer. It's 4 phosphorus atoms together. But as we'll see later, if you add something like sodium, or magnesium, or uranium, or helium, or whatever, those would all be just individual atoms. This reaction shows iron and chlorine coming together to make iron 3 chloride. And you can see once again, iron is a solid, chlorine is a gas, and you're making iron 3 chloride, which is a solid, kind of that orange solid that's kind of hovering there around the reaction. To figure out if a reaction has occurred, there are usually some telltale signs. You might feel heat change, either colder or warmer. Iron 3 chloride is definitely going to feel warmer. You feel very warm. You might see a precipitate form. A precipitate is a solid that forms. So iron 3 chloride here would be a precipitate. Some reactions you'll see a gas evolved. Some reactions you might see a color change. Some reactions, though, are very sneaky. You may not see any of those, and you have to be the hip chemist to know that a reaction is actually transpired. So this is a reaction now that shows methane, CH4, reacting with oxygen to make carbon dioxide and water. And notice that there's a 2 in front of O2 and a 2 in front of water. And those are necessary, all right? And I want you now to look at, though, the atoms, because CH4 has 1 carbon right there, the black atom. And on the product side, there's only 1 atom in CO2, 1 carbon atom in CO2. If you count up the number of oxygen atoms here, there's 1, 2, 3, 4. Each O2 has 2 oxygens, so 4 atoms total. And on the product side, there's 1, 2, 3, and 4. So notice that both the carbons and the oxygens are balanced on both sides. And sure enough, the hydrogens are white. There's 4 of them on the left-hand side, and each water has 2 hydrogens, so that's a total of 4. All of the atoms are balanced, all right? So this is what it means to have a balanced reaction. The atoms that go in will equal the atoms that come out. And if you have a mole of them or you have only 1 of them, it's no big deal. Chemists always want to use the smallest coefficients possible. So math people out there will realize that instead of a 1:1:2 ratio, 1 methane, 2 oxygens to make 1 carbon dioxide and 2 waters, you could also have 2:4:2:4, 2 methanes for every 4 oxygens, make 2 CO2s and 4 waters. But in a balanced reaction, chemists always use the smallest whole numbers, all right? Don't go to fractions, but smallest whole numbers are always the way to go when it comes to chemistry.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
This is a reaction that kind of stumped scientists for a while. They took mercury 2 oxide, HgO, heated it up, and in the process, O2 oxygen was liberated and only mercury was left. And they realized that what was left, like they had a mass measurement before and after, afterwards mass had been lost, and that kind of confused scientists for a while until they figured out that it was oxygen. Because the atoms are present in a reaction at the beginning and the end, the overall matter doesn't change. You might liberate the oxygen like it was here, or sometimes you'll gain the oxygen, but you're never going to have matter just magically disappear. So the law of conservation of matter states that all the matter that you start with has to be accounted for at the end of the reaction. You're not going to lose any, you're not going to gain any atoms. So chemists need to really be aware of what's going on. This is sometimes called law of mass action, same thing. Law of conservation of matter and law of mass action are the same. And again, it just means that all the matter has to be accounted for. You can't lose mass, you can't gain mass. Pretty simple, pretty cool, but also pretty powerful in the implications, as we'll see here in a little bit. Lavoisier realized that matter should be conserved, i.e. what you start with equals what you end with. And to that point, you have to have a balanced equation. And Lavoisier was the one that came up with this idea, and it's helped out scientists in so many ways. You probably have a cell phone. If you look at your cell phone, the plastic and the metals and all that stuff, they were all made through some kind of chemical reaction, and all the chemicals in your cell phone basically had to come through a balanced chemical reaction. So a chemist sat down someone made the chemicals. They then transformed them into the thing you see in your phone. So, woohoo, Lavoisier is cool.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs. The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for every 6 bromine atoms. It is visible as a white powder deposited on the beaker.
Okay, so let's pretend then that you are Lavoisier or some chemist back in the old days, and you took some aluminum, added it to pure bromine, which is a liquid, by the way, and you end up making aluminum bromide. Now, aluminum bromide is what they call a dimer. We won't talk about dimers so much right now, but if you look very carefully, those 2 little arrows right there are a different kind of bond, and we'll talk about that more later. But aluminum likes to bond with other aluminums. We'll see that more in a future lecture. For right now, just take it as a leap of faith that Al2Br6 is made. So if you wanted to make Al2Br6, the first thing you'd have to do is figure out how much aluminum you need, how much bromine. So we need to balance this reaction. Okay, well, bromine is a diatomic. That's one of the have no fear of ice clear brews. The brew is bromine. And aluminum is not on that list, so it's going to be an individual atom. So I would first start by balancing the bromine. There are 6 bromines on the right, but Br2 is just 1 on the left. So I would start off by putting a 3 in front of the Br2, because 3 times 2 would be 6 bromines, and we have 6 bromines on the right. I would put a big 2 in front of the aluminum because we have Al2Br6 on the right, 2 aluminums. And if you do that, you should be balanced. So to balance this reaction, 2 aluminums need 3 Br2s to make Al2Br6. Now on the bottom down there, you can see the actual atoms. So beginning, the aluminum's kind of the gold. There's 2 of them, and we need 3 Br2s. You can see there's 3 of these Br2 units. And the atoms on the left equal the atoms on the right. So the reactant atoms equal the product atoms. We are good to go. This is a balanced chemical reaction.
In the combustion of propane, a single propane molecule reacts with 5 molecules of O2 to produce 3 molecules of carbon dioxide and 4 molecules of water.
Propane is used a lot in barbecue systems. Propane is C3H8, and it reacts with O2 oxygen to make carbon dioxide and water. And this is another reaction that you can balance if you'd like to. First, you need to know what the reactants are and what the products are. And here, of course, that's going to be the C3H8 propane. Oxygen is O2. CO2 and water are made. Now, to balance a reaction like this, where you start to have more reactants and products, I try to leave the chemicals that are by themselves alone until the end. And for this reaction, that means O2. Because notice that all of the other chemicals in this reaction have a mixture of atoms, carbon and hydrogen, hydrogen, oxygen, blah, blah, blah. So we'll try to do the oxygen at the very end. So what I would do, the 3 carbons in propane are going to end up as carbon and CO2. So we could put a 3 right there, 3 CO2. And notice that there's 8 hydrogens in propane. Water has 2 hydrogens. So if I would put a 4 right there, I would then have 4 times 2, 8 hydrogens, which would balance the 8 hydrogens in propane. So now you can see that the carbon and hydrogen are good, but the oxygen still needs to be balanced. So on the product side now, you have 3 times 2, 6 oxygens from CO2, and 4 times 1, 4 oxygens from water. So 6 plus 4, 10 oxygens. Oxygen on the reactant side comes in pairs. It comes at O2, and if I need 10 of them, that means I'm going to put a 5 right there by the O2. So initially, I would have an invisible 1 by the C3H8, 5 in front of the O2, 3 in front of the CO2, and 4 in front of the water. And lo and behold, that's the answer. It takes 5 oxygens to react with 1 propane to make 3 CO2s and 4 waters. So this is an example of how you balance a reaction. And again, if you can do the atoms by themselves last, like oxygen in this case, a lot of times that makes it pretty handy. Another example is this thing. This is B4H10, a boron compound. It also reacts with oxygen. It makes a compound called boric oxide. You don't need to worry about that. That's B2O3, and water. So again, I'm going to try and leave the oxygen by itself, all right? Now, there's a little bit of a twist here I want to talk about. So first of all, we'll start off by, again, having oxygen at the end. If you look at just the borons, boron comes in 4, but B2O3 has 2 borons. So I'm going to have to put a 2 right there, because that will 2 B2O3s will have 4 borons, and that's what we have on the reactant side. Now for hydrogen and water, you can see that B4H10 has 10 hydrogens. Water comes in 2 hydrogen combinations. If you put a 5 right there, 5 times 2 is 10 hydrogens. B4H10 has 10 hydrogens. Good to go. But here's where the funky part starts. So the oxygens on the product side, you have 2 times 3 for boric oxide, that's 6 oxygens, and 5 oxygens from water. So 6 plus 5 is 11 oxygens. But oxygen has 2, all right, 2 at a time. And if you have 11 oxygens and you have to keep whole number ratios, which you do, that can be kind of difficult. What I would like to do is I'd like to put 11 halves right there, because 11 halves O2 would be 11 halves times 2. That would be 11 oxygens. But I can't do that because chemists always like whole numbers. It's a weird kind of thing. But if you get to this point, what you can do is just multiply everything through by 2. So I would have 2 B4H10, and instead of 11 halves, I would have 11 oxygens. And instead of 2 B2O3, I would have 4 of them, and instead of 5 waters, I would have 10 of them. And this is kind of a cool way to check yourself out. Now, if you're not feeling confident about it, let me share one more kind of trick with you. I'm going to have here an arrow which represents reactants on the left and products on the right. And I'm going to put in here boron, hydrogen, and oxygen. And the reason I write it on the arrow is I'm going to take a record here of how many atoms of each there are. And if the atoms on the left equal the atoms on the right, we'll be good to go. So using the purple numbers now, 2 times B4 would be 8 borons, and 2 times 10 hydrogens would be 20 hydrogens, and 11 oxygens times 2 would be 22. Now, if the numbers on the right-hand side are the same, we're going to be good to go here. So the B2O3, I have 4 of them, so 4 times 2, 8 borons. 4 B2O3s times 3 would be 12 oxygens. Water, 10 times 2 hydrogens would be 20 hydrogens, and 10 times 1 for water, 10 more oxygens. And lo and behold, the B's are the same on both sides, the H's are the same on both sides, and the oxygens are the same on both sides. And this is a trick you can always do to balance your equation. And again, my handwriting is horrible. I hate writing on the iPad. It's a personal problem of mine. But anyway, hopefully you get the idea. You can always check yourself by doing this kind of balance thing. And sure enough, that's exactly what we end up with. So this, again, is a balanced chemical reaction. You want to make sure that all the atoms on the left equal all the atoms on the right. So again, the 2 important things to pull out of this, actually 3, let's make it 3. First of all, there's an atom by itself, balance at last. So O2 was the last thing we did on both of these examples. That's definitely important. Number 2 is that if you get to the point where you have a diatomic and you need an odd number, you can pretend at first you have, like we did, with 11 halves O2, and then multiply everything through by 2 to give them whole numbers. That's another trick that really is handy. And then finally, if you ever feel uncertain about it, balance the atoms. Make sure that the atoms on the left equal the atoms on the right, just like we did in the last example. This is always stuff you can do. I do it myself once in a while when I'm not feeling confident. Nothing to be able to slow you down. You should be able to knock this out pretty readily. Here's a question you might see. It says the diagram below represents the reaction of phosphorus and chlorine to make phosphorus trichloride, and which statement is correct? All right. So first of all, you can see there's a big P4. Phosphorus is a tetramer. It comes in sections of 4. And you have then 6 little Cl2 interactions. Those are the green atoms on the reactant side. And on the right-hand side, you end up with 1, 2, 3, 4 phosphorus trichlorides. So if you look at all of these then, you want to know like which one of these is correct. And the first one says it takes 1 phosphorus atom and 6 chlorine atoms to make 1 PCl3. Well, that's not right because 1 PCl3 would have 3 chlorines. You don't want to have 6 chlorines. Now, likewise, if you look at the bottom one, 1 phosphorus and 6 chlorine atoms to make 4 PCl3s, that doesn't make any sense either. If you had 4 PCl3s, you'd need 4 phosphorus and you'd need 12 chlorines for that matter, so that's not right. However, if you look at B, the reaction needs 4 phosphorus atoms, and that's right, it's a P4, but it is 4 phosphorus atoms, and 12 chlorine atoms. 6 Cl2s would be 12 atoms, and that would create 4 PCl3 molecules, which is what we have on the right. I think answer B sounds pretty good to me. So anyway, this is the idea behind a balanced reaction, and it's just a way to make sure that you can make your products in as efficient way as possible. It may not be as tasty as cake, but it is the same idea, and it's nothing you shouldn't be able to knock out. Here's some hints about balancing reactions. Sometimes you'll see a little triangle over the arrow. That usually means that the reaction has been heated, all right? So if you see a reaction with a diamond over it, little triangle, that just means that heat has been added. So calcium carbonate breaking down to calcium oxide and CO2 will happen, but you have to add some heat to it. That's what it tells the chemist. Like I said earlier, sometimes it's nice to have initially a reaction with fractions, but then you can multiply everything by 2 in order to get it to have not fractions, all right? So initially, as a work template, if you will, fractions are okay, but chemists generally don't like using fractions. It kind of freaks them out. So in this one, if you had that balanced reaction with the fraction, you want to multiply by whatever is in the denominator, in this case 2. So you'd have 2 C2H6 and 7 O2s making 6 waters and 8 CO2s. That's also balanced, but you don't have fractions. Again, normally we stay away from fractions. There's one time in Chem 222 I'll talk about where we will need a fraction, but not in Chem 221, so don't use fractions. You want to balance the atoms that are by themselves last. So we saw O2 a couple times. We balanced it last. That's what you want to do, all right? So you try not to use fractions as coefficients if you can. You definitely don't want to change the subscripts. So for example, CaCO3 was calcium carbonate. If you needed one more oxygen, sometimes it's tempting to write CaCO4, but that's incorrect because carbonate's -2, calcium's +2. So you don't change the subscripts, but you can change the coefficients outside. So you have a lot of leeway when it comes to coefficients, but don't change the subscripts on the formula. If you end up with like a 2:4, 2:2 kind of ratio in your reaction, reduce them all by 2 to whole numbers, all right? That's always really important. We want whole numbers, not fractions, but smallest whole numbers. You can always check your answer by balancing reactants and products, making sure the atoms are the same. Charges have to be balanced. This is something that will help us later on. So if you have charges of +2 on -2, then hopefully on the other side you wouldn't have a charge of 0. We'll come back to that later. And practicing will make you an expert in this. Students usually do pretty well with balancing reactions. Just practice, make sure you're good to go. And of course, if you have questions on anything, let me know.